Today, inshallah, we will continue discussion about the magnetic circuit. And we described in the previous classes some solved problems on the different magnetic cores. We started with this shape of core. It's definitely a relay, consists of C-shaped core equipped with I-shaped core, and this I-shaped core, as you can see, it's connected to a fixed place by just a mechanical spring, and it's connected also to like a plate in order to make short circuit on two contacts. If the I shape is attracted to the C shape, it will make a short circuit on these two terminals. So this is the idea of the relay, and we discussed together that the amount of MMF consumed in the air gap is very high and depend on the length of the air gap. So if we have high length air gap, you will consume a lot of current. If you have a small length air gap, you will consume a small value of current. For instance, we started here at 1.5 millimeter, and the current calculated here was 4.19 amps. In the next example, it's assumed that the current was 4 amps, so it's less than the previous case, and you can see here the air gap length became 1 millimeter. So it's directly proportional to each other. Fine. Today we discussed also, I believe, this example last week. Sorry, last class. We discussed this kind of magnetic material. Have we discussed this problem, شباب ولا?
Not yet.
No, okay. So we'll start, inshallah, from this problem. Here, example 1.3 in the textbook. In the magnetic circuit of the figure below, the relative permeability of the ferromagnetic material is 1200. If the permeability is given with fixed number, this means we are going to operate the core at fixed permeability. So no need for curves anymore, and we assume that we are working in the linear part, for instance. Okay, so this is the value of permeability we are going to use in all of the problem. It's stated also here, neglect the magnetic leakage and fringing. So we will assume for all of time that the flux which is going to move from core to core through the air gap will be the same. So similar cross-section area for air gap and core, and same value of flux and flux density. All dimensions are in centimeters, so we need to convert to meter, don't forget, during calculation. And the magnetic material has a square cross-sectional area. So if you have this dimension here of this length of 2 centimeters, this means we have depth also of 2 centimeters. So the cross-sectional area here will be 2 by 2 centimeters, so it's 4 square centimeters. المطلوب determine the air gap flux, the air gap flux density, and the magnetic field intensity in the air gap. So we need phi, b, and h. In order to solve this kind of problem, we have firstly to recognize the dimensions. As you can see, the dimensions here are written on the core in terms of the length of some straight pieces like AB, like AF, like AE, like BE, and so on. And from the dimensions, you can see this is 50, 50, 50. So there is symmetry in the dimensions. This is going to be helpful in our problem. So why we need to recognize these dimensions? Because you have to calculate the average length which will be used for the flux. So we need to calculate, first we need to calculate phi. You know, we have only one relation used in problems up till now, which is Ni, which is the MMF, equals to phi multiplied by reluctance equals to h multiplied by distance equals to n multiplied by I, which is the value of MMF. So, in order to calculate B or phi or h, we need first to calculate the reluctance. And reluctance is nothing but L divided mu area. Mu for the core equals to the relative permeability, which is 1200, multiplied by the absolute permeability. So we have mu. Area, we know now the cross-sectional area for all of the core will be 4 centimeters. 4 square centimeters. So the area is given. Now we need to calculate the actual or average length for each part of the circuit in order to convert the magnetic circuit to the analogy of electrical circuit 1 in order to apply circuit analysis and calculate whatever needed. So simply we have two sources here. We have source at N1I and N2I. So there are two sources of MMF. So we expect by using the right hand rule, the right thumb hand rule, we can see that the flux based on the current direction here, the flux will move in this direction. In the other side, as you can see, the current is the same through the coil. So the current is moving in this direction. So if you used also the same right hand rule of Maxwell right hand rule, you can find the direction of flux, which will be also in the direction like that. So you have two components of flux. One is coming from this side, and the other is coming from the other side, and both of them will flow in the central limb. So this is the flow of flux in your circuit. In order to calculate that, you need to calculate the reluctances which face or limit the flux lines. So we need to calculate the reluctance in this part, which is the sides BA, AF, and AE, and also calculating the reluctance for BC, CD, and DE. And from the symmetry, it will be the same, because the same core, the same average length, and the same cross-sectional area. So the reluctance for the right part and left part will be the same. For the central limb, while the two fluxes are going to move here, we have two different reluctances. We have the reluctance of the core itself, which depends on the dimension BE minus the air gap length, okay, and the cross-section area is given also the same. And we have also the reluctance of the air gap, which depends on the the absolute permeability, because relative permeability of the air gap is unity, and the length is 0.5 millimeter. 0.5 centimeter. So now we have all of the data. We can calculate the reluctances for all of our circuits. So simply now we can convert to electrical circuit form. So this is the MMF, which is equal to I multiplied by N. As you can see, N1 equal to N2 equal to 500, and the current is 10 amps. So 500 times 10 amp equals 5,000 ampere turn. So this is for source 1 and source 2. Reluctance 1 and reluctance 2 are here, and the flux 1 and 2 are coming from the two sources and will flow in the central limb, which has reluctance of core, depend on the length BE, and reluctance of the air gap. So this is now the equivalent circuit. Right.
Doctor, your mic is muted.
Muted since long time or just now?
10 seconds ago only.
Yeah.
How? I don't know. It's a technical problem or what? But again, here, regarding conversion to the analogy or to the electrical circuit, as we stated, we have two different sources, each one equal to Ni. So we have N multiplied by I, which is 5,000 ampere turn here. And we have the reluctance of the left-hand side, which can be represented by reluctance BAFE, which depend on the length BAFE. And similarly, another reluctance for the right-hand side, and the two reluctances are identical because of the identical dimensions of the right one and left one. Regarding the central one, we have the summated flux moving here, and we have here two reluctances, one for the core and one for the air gap. How we can calculate the reluctance of the left hand side here, this lamp? Can you calculate the length with me? From B to A, what is the length, شباب?
50.
50 ولا
Oh.
50 ولا
52
52
52
52 صح؟ لأن هنا we have 2 centimeters, تمام? And here another 2 centimeters, and we calculate the average length. So from the center of this lamp to the center of this lamp. So the length AB now is 52. Right. Also AF. What is the length of AF? Is it the same?
The 52.
Yes,
52 as well.
That's fine,
Okay.
that's fine.
And you will find FE the same, 52. So we have 3 sides multiplied by 52. So simply the reluctance for BAFE can be calculated as L, which calculated as 3 multiplied by 52. طبعا we have to multiply by 10 to power minus 2 to convert centimeters to meter. And mu core, which is equal to mu node multiplied by mu r. Mu r, it's stated here, is the number is 1200, and mu node is constant 4 pi multiplied by 10 to power minus 7 multiplied by the area, and we could see that the area is 4 centimeters, so centimeters square. So to convert to square meters, we have to multiply by 10 to power minus 4. So this is now the value of the reluctance, 2.58 multiplied by 10 to power 6 ampere turn per Weber. طيب طبعا for the right hand side reluctance, it will be the same because of the identical dimensions. So we expect to have BCDE reluctance equal to BAFE reluctance. Regarding the air gap reluctance, it's nothing but LG divided by mu node AG. LG is given as 5 millimeters, so 5 multiplied by 10 to power minus 3, divided by mu node, which is 4 by 10 to power minus 7, multiplied by the area, which is the same, 4 multiplied by 10 to power minus 4. So this is the value of the reluctance of the air gap. تفضل.
The area is 2 or 4. It is written 2. Oh, okay.
2 by 2. 2 by 2.
Ah.
Okay. If you compare the value of reluctance of the air gap and core, you can find that the air gap reluctance is higher than the reluctance of the core. صح؟ يعني it's almost 4 times. تمام يا شباب؟ And this is not for the same lamp, it's for the long lamp. However, for the same lamp will be يعني much lower. As you can see here, the lamp BE, which is the central one, equal L of the BE, but for the core part, يعني excluding the part of the air gap, which is 0.5 centimeters. So the length will be 51.5 centimeters. You have to multiply by 10 to power minus 2, and this is the core permeability, the relative permeability, and the cross-section area. So now we could calculate all of the reluctances in our circuits. Type. If you need to calculate now the flux, simply you can construct any kind of electrical analysis, like Kirchhoff, like loop analysis, whatever the technique you can use. But you have to write the equation in the right way. For instance, we can take this loop, which is the MMF 5000 equal phi1 multiplied by all of the connected inductances, connected reluctances here, which is R reluctance BAFE plus reluctance PE plus reluctance G. Also plus phi2 multiplied by the central limb reluctances. Okay, so this is the equation using Kirchhoff. So as you can see, phi1 multiplied by all of the reluctance in the first loop plus phi2 multiplied by the branch in the middle equals to F1. Similarly, you can do the same for F2. However, from the symmetry here, we have phi1 and phi2, and it will be equal. You don't need to make analysis to see if the flux will be equal or not. From the first view, you can see that because of the identical parts of the magnetic circuit, we can conclude that phi1 equal phi2. Otherwise, if you cannot conclude that, you have to make the other equation for the second loop and solve the two equations together to get phi1 and phi2, and finally you will find both of them are equal. Okay. However, I mean, from the beginning, you can imagine that because of symmetry, phi1 will be the same as phi2. So, here we have only one unknown because phi1 equal phi2. So we can use only one equation to get the flux, and the final flux in the air gap, which is the required one, equals to 2 multiplied one of the two fluxes. So this will be the total flux moving in the air gap. Is there any question?
Doctor, the fluxes shouldn't be opposite in direction?
Why? If you return back again and apply Maxwell right-hand thumb rule, apply the rule here.
Okay, the flux will go up.
Exactly. Here. Can you see the current? The current is the same like that, huh? Okay. The same shape and the same direction. So the flux also is going to move in the upway. تمام؟
اوكي.
طيب.
دكتور الثلاثة في المعادلة من وين جت؟
Sorry?
3 في ال previous slide.
Previous slide here?
Yeah, 3 multiplied by 52.
Yeah, we agree together now we have 3 sides of equal length.
Yes,
Each one is 52, تمام?
Yeah.
Okay. So we got the value of flux in the air gap, and now we need to calculate the flux density. طبعا it's nothing but dividing the flux by the cross-section area, which is 4 centimeters, and we could find that the B equal to 1.034 Tesla, and the magnetic flux intensity in the air gap, we can get it by dividing B air gap by the mu node, which is 4 pi multiplied by 10 to the power minus 7. So this is now the amount of flux intensity needed in the air gap. تمام. طبعا شباب, if we change anything in the dimensions here, the equation, the core will not be in symmetry. This means you cannot assume that phi1 equal phi2. In this case, you have to solve the two equations together. Okay. For instance, the unsymmetry may come from considering the central limb here has a coil, and this one is left without coil. For instance, this is one shape. Okay. طيب.
دكتور.
تفضل.
If phi1 is different from phi2, how can we calculate the flux in the air gap?
Don't care about the flux in the air gap or the core. Now we converted the magnetic circuit to electric. Is it right?
Yes.
Use the circuit analysis. After using circuit analysis and getting phi1 and phi2, start looking for the air gap. You can see here the air gap, the flux which is moving here is the sum of the two fluxes. Okay. So the sum of the two fluxes, which is phi 1 and phi 2, is the same as the flux in the air gap. Okay? So yani, it takes the problem in steps. First, you have to recognize the dimensions. Secondly, convert the magnetic circuit to electric circuit. Third, solve with the electric circuit using circuit analysis. After that, you can get any missed data. Okay? طبعا يا شباب يعني we have many configurations for magnetic circuit. Is there a question? Okay, خلاص يعني if I shared with you the reference here, can you see this is a different shape? Okay, but this is regarding the EMF and transformer. This is for instance, okay, you have two coils, okay, and one يعني core, okay, with air gap, and it may be assume that N1 and N2 are different, and two different coils. ماشي. Here you have different shape, okay. Here as well you have E shape with I shape. تمام. And as you can see here, the length of the I shape is not the same. So should we take the length of all of the bar, or the effective length which is going to move according to the length of the E shape? We have to consider that. Yani take care, if we have the length of I shape here, yani for instance, the upper one, we can see here 10, 20, 20, 20, 10. So we have 80, assume this is centimeters, 80 centimeters, and the effective length of this part of the upper part will be only 70. صح كده يا شباب? So this will be 70 centimeters, and this one here is 50. For the average length, you will lose 5 centimeters from here, so you have 45 here. So you have to add this one multiplied by 2 plus that one. So what will be the equivalent length in the lower part here? Is it going to be the overall length, or just the length that the flux is going to move here, like the upper one? Which is right, Shabab? And we calculate this one as 70. The upper one here, the average length is 70. So how?
It will be like the upper one.
Exactly, same. Because this will be the effective length that the flux is going to move. So don't care about all of the dimensions. We care about the dimension of the track that the flux is going to move. تمام يا شباب؟ Also, we have another shape here for DC motor, I believe, or reluctance motor. And here we have different shape, so with different air gaps. So this is not any symmetrical one, تمام? Because we have two different air gaps. يعني I urge you to يعني train yourself for all of these problems, and يعني if we have time, inshallah, after finishing the required parts in the syllabus, we may solve some extra problems, inshallah. تمام? But يعني you can train yourself now يعني thinking about this kind of problems. So we could now discuss this problem, and I believe this problem is simple because of symmetry. Now let's go to another important topic, which is the inductance. Firstly, if I would like to buy inductance, how can I get it? يعني you know, we can find electrical elements in the market like resistance, like capacitance. However, for a power inductor, not the small one which is made for specific products, for a power conductor may be needed for a motor, for instance, for any actuator, for any application, you need a high power inductance. How you can get it? Actually, you may not find it in the market. you have to create or ask a company to create it for you. Type. So what is the, or how we can create an inductance? Inductance is nothing but coil, which is wires with a certain cross-section area and manufactured in a certain way, and it has insulation on the top of it, okay, and it's wound around a core. This core is a ferromagnetic material, and the magnetic material is different according to the frequency of current, and we are going to discuss it inshallah in this chapter. So we may use high frequency cores, so we may need ferrite core instead of the cast steel one, for instance. If the frequency is small enough, we can use the cast steel, cast iron, whatever, okay? And after connecting that, we need to calculate the inductance. How to calculate the inductance? Simply, we can connect these terminals to an LC meter and start measuring the value of inductance. Here, or if we have air gap, we can start making air gap by adding spacers in an air gap in order to fill the magnetic air gap with different materials in order to get a certain value of inductance. Fine. What are the factors that can we control in order to control the inductance? This is what we need to drive now. If you have the flux linkage, which is lambda equal to n phi, and phi, we know that phi is the flux and n is the number of turns. The value of inductance, L, equal to lambda divided I. But we need to calculate L as a function of the parameters we have, not depending on the value of current. We need to calculate the inductance based on the materials we are going to use, the wire itself, the core, okay? So let's simplify the equations to get the main parameters of inductance. So if you now divide lambda divide I, so n phi divide I, and phi is nothing but b multiplied by the cross-section area, and the cross-section area is a function of the core itself, so it's good. Now we are turning to the parameters. So nba divide I, then b equals mu h, mu, which is the relative permeability, multiplied by the absolute permeability. Now we have h and h and I, and we need to remove also these two parts to keep all of the equation depending on the core and winding itself. If we substitute, is there a question, Shabab? Right. If we substitute this equation here, you know now the n mu ha, n mu ha, I. If you use the equation of HL equal Ni, you can replace I by HL divide N. Now you have H in the numerator and the denominator. You can omit H from both sides. And also you have N here in the denominator of the denominator, so you can put it in the numerator as N squared, okay? And you have mu and area here. You can move it to the denominator to be L divide mu area. So now the relation N squared divide L divide mu area, and you know L divide mu area is nothing but the reluctance. So finally, we can say inductance equal to N squared divide reluctance. And as you can see now, N squared, N depend on number of turns, L area depend on the dimension of the core, mu depend on the material of the core. So now the inductance equation is only depend on the core and number of turns. So we can design based on that. We can design based on the number of turns. As you can see, if you would like to increase the value of inductance, just make more windings on the magnetic circuit. If you need to increase also the inductance, you may use a higher air gap. lower air gap. تمام. But if you would like to reduce the inductance, you can reduce N and also reduce the increase the reluctance and so on. So these are the parameters used to tune or to reach to the required inductance value. تمام يا شباب. طبعا there are some devices can measure the inductance. It's called LC meters, and we have these inductances, these devices in our labs in KFUB. Here is a simple example for the inductance. Firstly, we have a magnetic circuit of figure 19, which is this one, N equal to 400 turns. The mean core length is 50 centimeters. The air gap is 1 millimeter. The cross-section area of core and air gap are equal and equals to 15 square centimeters. The relative permeability is given at 3000 and the current is 1 ampere. Find the flux and the flux density in the air gap and then calculate the inductance of the coil. طبعا the first part we solved it like this before. You can calculate the reluctance of the core, L divide mu r mu node area, and all of these are given. Reluctance of the air gap similarly, L divide mu node area, and as you can see the value here is 530 multiplied by 10 to the power 3, and here is 88. So as you can see, the reluctance of gap is higher than maybe more than 6 times or 6 times of the core reluctance. We need to calculate flux, so simply we can say Ni divide summation of reluctance. N is given 400, current is 1 amp, so the reluctance also are calculated, so we can calculate the flux. And similarly, we can get the flux density by dividing phi divide A and get the value of flux density. So this is the same like previous examples. Now we need to calculate the inductance, so simply we can say inductance equal to N squared divided reluctance, and reluctance is here, which means the summation of the two reluctances. As you can see, this is the core reluctance and this is the gap reluctance, and this is the value of the inductance now, 258 millihenry. Okay. By the way, this value is high. طبعا value of inductance depend on the application you are going to use. You may need high inductance, you may need low inductance. It's up to the design of your device or your machine. Okay. However, for machines, we may have very small inductances compared to this value. Several millimeters, not hundreds of millimeters. Okay, this is for small rating machines. However, for high rating machines, may be different a bit. Right. A question here. Now this is the inductance. If you would like to decrease the inductance, what can you do in the air gap? Decrease the air gap or increase the air gap?
Increase it.
Right. So if we increase the air gap reluctance, okay, you will get smaller L. However, increasing air gap will consume more current. Is it right? So instead, in order to reduce the inductance, you can reduce the number of turns. تمام? So this is a better solution, because if you increase the air gap, you will increase the MMF required, and this will take you to increase the current as well. However, if you decrease the N, in this case, you can find that the inductance will be lower. طبعا another way to calculate inductance is lambda divide I. The same. You have N, you have phi, and you have current as well. You can calculate it based on the electricity parameters like flux and current. تمام. Is there any question, شباب?
دكتور.
تفضل.
Is this 1.16 with us? Because in the syllabus is not.
Yeah, it's not exist in the syllabus. You are right. But because it's very important and it will be useful to describe it here, because we are going to use in all of machines during this course.
Okay.
يعني it's not in the syllabus but يعني I believe it's important for you even يعني later إن شاء الله in your life. يعني it's very important to know what's the meaning of inductance. يعني firstly let me stop the يعني